Phosphine has the chemical formula pH₃. Phosphorus is in the fifth column of the periodic table, so it has 5 valence electrons. Each of the hydrogen atoms has 1 valence electron. Therefore, in phosphine, we have a total of 8 valence electrons that we have to allocate. We need to satisfy the duet rule for each of the 3 hydrogen atoms, and we need to satisfy the octet rule for phosphorus. And we're able to do that. We also notice from the card that since there are additional holes that aren't shaded gray, that for phosphorus we are able to expand the octet if that's necessary. In this case, it isn't because we have precisely enough electrons to satisfy the octet rule. We also might recognize that phosphorus is in exactly the same family as nitrogen, and we can think of phosphine as being a sort of phosphorus analog of the incredibly important compound ammonia. Ammonia is a gas, phosphine is a gas, but there's a very important difference between the two compounds. Nitrogen is one of the 4 very electronegatives. We call that fluorine, oxygen, nitrogen, and chlorine are so electronegative that when they combine with hydrogen, they get a disproportional share of the electrons, so that they get a partial negative charge, and that the hydrogen atom then get a partial positive charge, and then we have the phenomenon of hydrogen bonding. The properties of ammonia are very heavily influenced by the fact that ammonia can hydrogen bond. Therefore, ammonia has a much higher boiling point than we would predict based upon the number of electrons in the compound, which would influence the London forces. For phosphorus, on the other hand, is not one of the electronegative elements, the very electronegative elements. Therefore, in phosphine, we do not have the phenomenon of hydrogen bonding. Therefore, phosphine actually has a lower boiling point than does ammonia. Arsenic is in the same family as nitrogen and phosphorus. So we might predict that we might be able to make a compound with arsenic that is analogous to ammonia and analogous to phosphine. And that is absolutely true. And that gives us the gas AsH₃, which is called arsine. Arsenic has 5 valence electrons. Each of the hydrogens contributes 1 valence electron. Therefore, we have a total of 8 valence electrons in the compound. We can satisfy the duet rule for each of the hydrogen atoms, and we can also satisfy the octet rule for arsenic. And we have no need to expand the octet, even though, since arsenic is in the 3rd row or below, we could expand the octet if it were necessary. Arsine is important because it is the basis of, among other things, it's a toxic gas, but it's a key intermediate in a forensic science test called the Marsh test. And it's a method of determining if a person has been poisoned with metallic metal arsenic. Arsenic acid has the chemical formula H₃AsO₃. Each of the oxygen atoms contributes 6 valence electrons, so that gives us a total of 18 for the oxygens. Arsenic contributes 5, and each of the hydrogen atoms contributes 1. That gives us a total of 26 electrons for the entire system. We can allocate the electrons in such a way that we can satisfy the octet rule for each of the 3 acidic hydrogens. We satisfy the octet rule for each of the oxygens, and we have just enough electrons left over to satisfy the octet rule for arsenic without needing to expand the octet. If we abstract all three of the acidic hydrogens from Arsenous acid, as for example by reacting with a strong base, they leave their electrons behind, and we are left with the Arsenite ion. If we had to generate the Lewis structure for the Arsenite ion, AsO₃ 3- de novo, we would recognize that we had 3 oxygen atoms. Each contributes 6 valence electrons, so that's 18. The arsenic contributes 5, so we have a total of 23 electrons. And then we notice that the ion has a -3 charge, which means that we need to add 3 more valence electrons for a total of 26. And we notice that 8, 8, and 8, we satisfy the octets for each of the oxygens. And then we have 2 electrons left over, which are just enough to satisfy the octet rule for arsenic. The other important oxo acid of arsenic is arsenic acid, H₃AsO₄. Here we have 4 oxygen atoms. Each contributes 6 valence electrons, so that is a total of 24 electrons. The arsenic contributes 5, and each of the 3 hydrogen atoms contributes 3 more. This gives us a total of 32 electrons for the entire system. And we notice in this case, one difference between arsenic acid and Arsenous acid is that since we have 4 oxygens, one of the oxygens is not bound to a hydrogen atom. Typically in oxo acids, these oxygens will be double bonded to the central atom, and that is what we have here. And if we allocate the electrons to satisfy the octet rule for each of the oxygen atoms, we notice that gives us 4 times 8, which is all 32 electrons. In the process, we are able to satisfy the de Wet rule for each of the hydrogen atoms, and we satisfy the octet rule for arsenic. But not only that, we notice that for the arsenic we have 2, 4, 6, 8, 10 electrons. So for this particular arsenic compound, we are actually required to expand the octet for arsenic. And we're able to do that because it's in the 3rd row or below. It has d orbitals, at least ostensibly, available for bonding. If we react arsenic acid with a strong base, we can abstract all 3 of the acidic hydrogens. And if we do that, the hydrogen leaves, but its electrons remain. So if we do that, we're left with the arsenate ion. So arsenate is AsO₄ 3-. If we are just trying to derive the structure of this ion without having started with arsenic acid to begin with, we would notice that we have 4 electrons for each oxygen. So that's 24 electrons, plus 5 more from arsenic, gets us to 29. And then, since the ion has a -3 charge, that gives us a total of 32 electrons. So that gives us 8, 8, 8, and 8. Now for this case, we're not going to go through all of them, but you notice that we have 3 single bonds of oxygen to arsenic and 1 double bond. At the very least, there's no reason why this particular oxygen atom should be the double bond and this one isn't, for example. So we could just as well have moved the double bond to any of the other 3 oxygens to generate a total of 4 equivalent resonance structures. Also, we would notice that there's the possibility of replacing the double bond arsenic to oxygen with a single bond. So that essentially we had a structure with 4 single bonds. That would also be a valid resonance structure because we would satisfy the octet rule for each of the oxygens, and we would satisfy the octet rule for arsenic. So the true structure of arsenate is a combination, a sort of average of all the valid resonance structures, of which this is just one.